Fourier transform is an important mathematical concept that we will attempt to explain visually. We begin with the Fourier series. The equation for the Fourier series states that a function can be written as a linear combination of sinusoids, which are cosines and sines. For example, here our function is a square wave. The first approximation is the first term in the Fourier series, which occurs at a frequency of 0 Hz. This essentially just means it averages over the function and is a straight line. A second approximation occurs at a frequency of 1 Hz and looks like a sine wave. As you can see, this better approximates our original square wave. Adding a third term at a frequency of 2 Hz gives us an even better approximation. As we add more terms, we would receive better and better approximations of our original square wave. From here, we move on to the Fourier transform. The Fourier transform essentially does the same thing as the Fourier series. It takes a function and turns it into a linear combination of sinusoids by summing them over an interval. When we apply the Fourier transform to a function of time, we get an output as a function of frequency. You might be wondering why we would want to take a function of time and transform it into a function of frequency. As we stated earlier, the Fourier transform breaks down a function and turns it into a linear combination of sinusoids. Turning it into a function of frequency, we find the constituent sinusoids that make up the original function in time. This is possible, again, because the time and frequency domains are mutually orthogonal, which means they occur at 90 degrees. In the frequency domain, we can find the amplitude and frequencies at which the constituent sinusoids occur. By summing all the sinusoids at the respective amplitudes and frequencies which the frequency function gives us, we return back to our original time function. We stated earlier that the Fourier transform can be applied to any function to find its constituent sinusoids. However, not all of the constituent sinusoids are always going to be in phase, and we use what is known as a phase shift. So what exactly is a phase shift? A phase shift simply means that we are going to start the constituent sinusoids at different points in their cycles so that when they are summed, they are constructive and destructive at the appropriate points to return us to our original time function. For example, we might start this sinusoid here, and this sinusoid here, and this sinusoid there to receive the function that we are looking for. The complex plane is a useful tool for helping us to visualize Fourier transforms because Fourier transforms simply break functions down into their constituent sinusoids, and sinusoids are simply circular paths. The complex plane is very good at plotting circular paths due to Euler's formula. This image better breaks down the relationship seen in Euler's formula. Here, in the complex plane, e to the I theta is plotted. We can see that in the imaginary versus time axis, we have its sine wave, and here, in the real versus time axis, we have its cosine wave, which is exactly what Euler's formula states. Again, this is exactly what Fourier transforms do. They break down functions into their constituent sinusoids. The complex plane simply helps us visualize this. The discrete Fourier transform allows us to use the Fourier on a vector of discrete points instead of on a function. Any function of time has a corresponding curve in the complex plane. If we don't have the time function and instead only have a curve in the complex plane, then we simply move around the curve in the complex plane starting at theta equals 0. For each theta step we take, we plot the corresponding point on the time plot. We now have a vector of points in time that we can use the discrete Fourier transform on. This will output a vector of points in frequency that we can use to plot in the complex plane as a series of circles. The series of circles correspond to their own sinusoids in time that will sum up to our original time function. The curve, on the other hand, is what the circles will trace around. Any curve in the complex plane can be broken down in this way, including Homer-Simpson. Taking discrete points along a curve of Homer and applying the Fourier on it allows us to trace out Homer using the circles that we found using the discrete Fourier transform. Here is a video showing exactly that.